You are the presenter?
Yeah,
Yes.
first presenter. I don't know how to put it on directly.
No, you can't, because
Oh.
actually we are streaming the session to the remote.
I see. So do you have a stick? I can
Yes, 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 yes.
Yeah.
It's a PowerPoint, PDF?
Yes.
Yes.
PowerPoint.
I do have a dongle.
Hey, good to see you, John.
Good to see you.
Yeah.
We have a USB stick for transferring files. Yeah, well, why don't you go up? Shoot. I can't find it right now. There you go. So glad you could make it.
Singapore?
Yeah, yeah. It was a long ways. Yeah.
Also beautiful locations. The conference, if you're going to travel all the way across the world, might as well be just
They weren't able to change the display on this thing.
Okay, good.
Oh, okay. I noticed something on
Yes, good, good, good. Screen.
Oh, is that right? Oh, it was showing the speaker's face instead? Okay. But we had the recording. Okay, but not the video. Well, we're going to have to ask Professor Hajimiri to give a talk again.
Can do it after the banquet, you know.
That's right, that's right. Yeah. But no, before the banquet. In order to get into the banquet, you had to record again. It's what's the display on here?
The display is a second display.
Do you want to use the HDMI again? It worked for me yesterday.
It worked for HDMI and VGA, but actually this laptop is on.
I see.
When we changed the spec.
That's why you weren't able to get the video.
Yes,
Yeah.
In 5 minutes I was so.
No.
My brain did not work.
Understandable.
Let's have a look.
Maybe for backup, we can check if the display can be changed. So the
recording, the screen recording is on this device, right?
No, I think it's extended the things. I don't know, you want the thing? I can try to give you the thing.
Oh, okay, that's right.
Great.
Hold
Yes. The one being shared because it's a lot.
Vintage, like a rock.
military issue or something.
Control C.
Did you come down to the frames just for this conference?
Pretty much, yeah. No, I'm going to try to combine it.
We're really honored you.
No, I appreciate the invitation. It's a great community to kind of interface with, because we're not kind of experts in wireless power, so it's just difficult with these conversations.
For sure. I think we're, super interesting application.
Yeah.
That's no better person.
Yeah. So how's everything in Singapore? I'm trying to remember when you left Stanford.
Yeah, it was 7 years ago. So it's been quite some time.
So it's a 10-year process?
I just finished it.
Okay.
Yeah, so that's why I'm out here.
Some people take a year off after that.
I never get a year, but
Yeah.
at least a conference. This is the first travel I've had almost in 3 years. Quite a relief to get out of it.
Yeah.
Test the video again?
Yeah, we got to just back out.
So it's okay?
Yeah.
So you will just have to switch it, you will see your slide on the next slide, and everything will be straight normally. I will check the screen on this computer.
Okay.
And I will send an announcement for the others.
Is it now? Yeah, exactly.
What time is it this morning? Hello, yeah, hey, nice to meet you. Nice to meet you. Thank you for coming. I'm so glad to be here. So, this is like the co-generation. So,
You want to open up some screen again?
yeah, apology, very basis, Can I go ahead and pull out the stick, or is that?
You can remove your stick, yeah, let it unplug it for you. It's in French,
Crash. Every time, 3 minutes to spare.
The man yesterday was too good. Simon, which time you want to start the session?
I remember from Simon,
Do you want to delay the start of the session or do you want to start at 8?
That's usual, 8.
Okay, I will send an announcement. Just be there and wait for 20 seconds.
Yeah. She's been. Yeah. I remember she moved from UMI, it must have like accelerated.
Yeah, I mean, I've only been here 3 days. About the same time I did.
Okay, yeah. That's probably, she probably owes you something for that. Yeah. I don't know her very well.
It's very, it's
very,
I really enjoy it. Yeah. Great disregard.
You were first off those sort of papers I saw. I don't know, just because you were like super productive or super small.
Actually, it's an interesting dynamic when we first came in. She had this like sort of theoretical. There's like a great student, you really need someone to help like. So I sort of came in and I loved writing about it.
That's how you come up to speed, yeah.
Sort of roll from there and after we did that, oh, we really should.
Yeah, that's right. Similar approaches in terms of why. So are you still kind of sort of Asian space? It seems like just starting Yes. Okay, yeah. Just yeah.
Et comment ça se fait en marche, le micro?
Celui-là, je les ai vérifiés ce matin.
Oui.
Oui, il marche.
Ok, c'est bon. On va devoir créer. Ok, on va lui. On va mettre pour les deux. Ouais. Donc, je vais faire quelque chose, donc c'est.
Hello everyone. Thank you for coming this morning after this awesome evening that we had in the submarine pen yesterday. I hope that you got the chance to see the true, real operating Enigma machine, the special version that was used in the submarine from those U-boats. And the people from the Crypto Museum, the two curators of the museum are still here today, and they will present some backscattering-based, wireless power-based devices that have been used during the Cold War for spying. So this will be today very close during on the exhibition floor. So I invite you not to lose the opportunity to have a check to this wonderful gadgets that they are. We are going to meet this evening at Place de la Bourse. Make sure that you have your green ticket. Green ticket is a way for you to enter the venue. This will be even greater than it was yesterday, so I invite you not to miss this great evening. If you don't have a green ticket, or if you know already that you won't be able to make it, I'm inviting you to go to the registration desk and to verify that everything is fine for you. I'm also inviting you to use this jas that you have in your bag. We are trying to reduce as much as possible any kind of landfill waste. So if you feel comfortable using it, please do so throughout the conference. In this way, there will be less stuff to throw away. We are probably going to have the wine and cheese on Friday, and for this, I'm reminding you that there is a WUVA poll that is ongoing. So if you know already that you are coming or that you are not coming, please make sure that you check this poll for the wine and cheese. So that's all for today. Thank you for being here, and I'm sure it will be a true awesome keynote. It will be a true awesome session, and today is going to be wonderful. So I'm handing over to John, who will introduce our speaker.
It gives me great pleasure to be able to introduce our keynote speaker for today. Our speaker is none other than Professor John Rogers. Professor Rogers is the Simpson Query Professor of Materials Science and Engineering, also biomedical engineering, and also of medicine at Northwestern University, where he directs the Institute for Bioelectronics. It's not without exaggeration that if I were to read all of his awards, I'd eat up a significant fraction of his time. So I'll just name one of them. He is one of perhaps just 25 people ever to be simultaneously elected to all 3 U.S. National Academies of Science, Engineering, and Medicine. So a central question we've been thinking about in this conference so far is when wireless power is going to be more than just a gimmick and really change the way we do things in everyday life. The answer, which is both obvious and also really hard, is when we find ways to use wireless power to address real human needs. And I think we're really fortunate to have Professor Rogers come here and speak about these needs. There's really no one else who could bring better insight on how this technology can be used in the field of human health. So with that, let's welcome Professor Rogers.
Great, thanks, John, for that kind introduction. I don't think he and I have ever met in person, but I'm a big fan of the research that he did when he was at Stanford and now on the faculty at the National University of Singapore. So it's a great pleasure to be here and to get a chance to interact with John and the rest of the group here. So as John mentioned, I run sort of biomedical engineering group at Northwestern. We're very focused on translation, so trying to figure out what kind of advances in engineering science can lead to technologies that have broader impacts, mainly on human health, either directly as devices that deploy on the human subjects or indirectly through platforms that enable new options in biomedical research on animal models. And so I'm going to step you through in the next 45 minutes or so a number of different technologies that we've been working on in that general space that have as a key feature, they exploit wireless power. So these are battery-free wireless systems, and it's really an essential feature of all of the devices that I'll talk to you about. But it's very much application focused, very high level. I'm just going to step through a number of different platforms where we have good commercial traction or devices that we think could have potential for use in a commercial mode. But I suspect, given the expertise of this audience, you're going to take a look at what I'll present to you, and you're going to say, wow, that's really trivial sorts of approaches in wireless power transfer. And I would agree with that. So my expertise is not in the wireless power transfer component of the work, but it's an essential part of it. And so what I hope as a consequence of this presentation and the interactions that I hope to have with many of you in the audience is that there may be opportunities for collaboration, joint projects where more sophisticated technologies in wireless power transfer could really enhance the sorts of platforms that I'll share with you today. So anyway, that's a bit of a long-winded context, to just set the stage for what I'll talk to you about in the next 40 minutes. So there's sort of three areas that I'll share with you. One is in vital signs health monitors, primarily for beginning of life health challenges. So maternal, fetal, neonatal, pediatric health. I'll give you a sense of what we've been doing in that area. It's sort of skin-like wireless devices, again, battery-free systems for that domain of use. And then as an extension, thinking about not only sensing, but providing feedback to the patient through haptic interfaces also that can operate in that battery-free manner. So this is sort of in clinical healthcare. That would be sort of the first area that I'll talk to you about, monitoring primarily, ICU type applications. And then the second will be in platforms that enable new forms of biomedical research on animal models, in particular using optoelectronic neural interfaces to understand how the brain works, essentially, and how the peripheral nervous system transmits information to the brain, and I'll give you a sense of that. So good commercial traction here. We have commercial products used worldwide in both of these spaces. And then I'll conclude with sort of a look at over-the-horizon opportunities that we think will be important in the future, but today don't have commercial embodiments, but those where we think the potential is there in the relatively near-term future. And that is in this space of bioresorbable electronics, so temporary medical implants that offer electronic functionality over a clinically relevant time period and then eventually resorb and disappear into the body, much like a resorbable suture, but differentiated from sutures in the sense that the platforms have full electronic functionality. And I'll focus primarily on pacemakers, but we also have wireless peripheral nerve stimulators to accelerate rates of neuroregeneration, healing from damage that can occur to the peripheral nervous system. So in general, what we're contemplating here are soft forms of electronics. So moving away from rigid planar designs in silicon CMOS to technologies that can offer that level of sophistication, but in physical forms that more naturally, chronically, without adverse effect, can interface with soft, moving, living tissues. And you might think about that in the context of the human brain, biology's most sophisticated form of electronics. You might want to bring to bear to that problem. You want to understand how the brain operates. You want to develop sort of electrical stimulation approaches to treat various brain disorders. You might want to bring to bear to that problem man's most sophisticated form of electronics, the silicon CMOS integrated circuit. But you might imagine that there are very, very difficult challenges in achieving that integration just due to the radically different physical properties associated with the textured surface of the brain, very soft, low modulus material, and the characteristics of the silicon wafer. So beyond just the materials level biocompatibility, you have to think about shape and geometry and mechanics as well. And if you could solve that problem, you wouldn't stop there. That same kind of soft brain-compatible electronics would allow you to interface electronic technology with other vital organs of the human body. So we've done a lot of cardiac interfaces, bladder, kidney, spinal cord, peripheral nerves, and also the skin, which is the largest organ of the human body. Skin-like electronics might also be an interesting technology in the future for digitally enabled healthcare. And so the challenge from a material science standpoint is how do you convert this into something that has tissue-like characteristics? And one way to go might be to look at this kind of platform, acknowledge the radical differences in physical properties compared to living systems, and abandon materials like silicon and gallium arsenide and gallium nitride and copper and silicon dioxide and so on, all these rigid planar inorganic materials as they exist in these kinds of platforms, and try to replace them with 2D materials or carbon nanotubes or polymer-based semiconductors. And that would be one route to go. And we spend a lot of time in that direction. There's still a lot of academic groups exploring that route, but the difficulty is, in order to do something meaningful, you would have to essentially reproduce the kinds of manufacturing infrastructures and approaches that have developed around, the silicon based IC technology over the last 50 years, and that's a pretty daunting path to contemplate. And so the other way to think about it is to kind of stick with the established materials to the extent possible, but deploy them sort of in a hybrid format. So mix and match them with soft materials in sort of a smart way in terms of the layouts to give you effective mechanical properties that are matched to those of biological tissues, but in systems that incorporate high modulus materials. And so that's turned out to be the most effective way for us to develop a biocompatible electronic, or just more generally microsystems technology, not just electronics, but optoelectronics, microfluidics, microelectromechanical systems, photonic systems can all be engineered in this way, where we take these hard elements, thin them down so that they're mechanically flexible, and then interconnect them with these sort of filamentary serpentine type structures, embed the whole thing in a soft elastomer. And if you do that with quantitative attention to the details of the mechanics of how these hard, soft, hybrid material systems come together, you can achieve effective material properties, modules in particular, that are matching those of nearly any soft tissue system in the human body. So I won't say much more about that, but there's a whole tool set for doing that. We felt like we sort of figured it out, more than 10 years ago by now, and then got a little bit more sophisticated in 2014, and then probably 2015, 2016 onward, we really focused on leveraging this kind of unique technology to address unmet clinical needs, and I'll describe a few of those in the next slide. So you really think about these devices as skin-like pieces of electronics that can interface directly with the skin to establish physical contact that's needed to support all sorts of measurements of vital signs that are done routinely in a hospital setting, but with wired systems where the electronics is kind of removed from the body interface, and the sensors are the only things that interface with the skin, and the ability to do continuous monitoring in an ambulatory setting of those kinds of technology is highly limited, whereas this sort of platform can go onto the skin, physically imperceptible. You can imagine continuous ICU-grade monitoring in a home setting, and that's kind of the vision around what we're attempting to do and have done in certain cases. Now the key question is how do you power this thing? So this particular platform has the antenna out here as an inductive coil. It has arrays of silicon MOSFETs, LC oscillators, strain gauges, temperature gauges. This sort of platform to demonstrate the different kinds of components that you can integrate in this skin-like platform. The big question is the battery. A lot of this stuff miniaturizes, the battery doesn't. To first order. It doesn't act nearly as aggressively as the electronics. And so that's where the need for wireless power transfer comes into the equation, because if I drop a battery into this platform, I really destroy that kind of essential skin-like mechanics, which is a critically important feature of the technology. And so if you think about different ways to get rid of batteries and replace the battery power with a wireless power source, maybe you can think about different modes for doing that. There are different schemes where you can convert mechanical energy into electrical energy, sort of kinetic. You think about acoustic waves or just gross mechanical motions, and the device type in that case would be piezoelectric or triboelectric generators. The problem is it's pretty intermittent, and so it's hard to get a reliable source of power. So if you have a power storage capability in your device, maybe you harvest over time and then you draw down the power as needed. But to rely purely on kinetic sources, mechanical harvesting strikes me as pretty difficult in that sense. And then the other class that you might think about, electromagnetic, optical, photovoltaic in that case, again, great way to think about harvesting, but it only works if the lights are on. And so, again, sort of intermittent, and maybe you could combine, kinetic with optical and do something and sort of smooth out the variations in power they have available, but that's also practically pretty difficult. And then you can imagine radio wave approaches, either far field or maybe midfield, or coupling, or near field inductive. And so, as I mentioned at the outset, you're going to take a look at this, you're going to see, wow, that's really simple in terms of the power harvesting strategies, and I will fully admit to that, because this really works, for lots of applications we're interested in. I mean, it could be better, and we would look for opportunities to improve, the operating range and so on. But for all of the applications I'll talk to you about, really using resonant magnetic inductive coupling, in many cases at the NFC standard frequency of 13.56 megahertz. In other cases, we move away from that particular frequency, but the underlying physics is, for everything I'll talk to you about today is based on magnetic induction. So let me talk then about applications. Forget about base technologies. What do you do with all of this stuff, and what kind of needs can you address, and what kind of patient lives can be improved with these sorts of approaches? And we decided that this was the most compelling opportunity for a wireless, battery-free, skin-like vital signs monitoring technology, and that is in the context of premature babies. So if you have experience with this, you will recognize this picture is fairly familiar. This is what goes on in the neonatal intensive care unit. So these are very fragile patients. They're premature. Their prematurity leads to the sort of fragile nature of the health status, and as a result, you need to do 24/7 full vital signs monitoring. So that's heart rate, respiration rate, core body temperature, blood oxygenation, and then intermittently, if necessary, blood pressure as well. And the way that's done today is with hardwired interfaces to external boxes of data acquisition electronics with terminated biosensors with interface to the skin of the infant with tape. And these wires have to be removed and replaced typically in a 12 or 24-hour cycle so that the babies can be cleaned, the diapers can be changed, this sort of thing. And because the skin is not very well developed at this stage of their lives, removal of that tape can sometimes damage the skin and lead to scarring and injuries in that way, which is a big disadvantage of this kind of primitive engineering approach. The other complication is that the wires themselves, the forces that they impose on the baby and the weight loading on the baby's motions really restrict the natural ability of the babies to move around. And then the third consequence of this, which we didn't really appreciate until we got deep into this project, is that those wires also frustrate the ability of the parents to interact with their child. The wires getting in the way of that. And that's sort of a tragic thing because it's known and it's been proven that skin-to-skin contact between a baby at this age of their lives and the mother or father, for example, has a very strong therapeutic benefit on the way that the baby develops. And so the idea of this is just a Photoshop drawing that we put together, just to give a sense of where we want to go to the students who are working on the project, is to remove all of this stuff, get rid of the rat's nest of wires, get rid of the invasive tapes, and replace that with 2 or 3 of these wireless battery-free skin-like devices to reproduce all of the vital signs without any sacrifice in data quality, but in a way that's much more well-aligned to this class of patients. So we're able to do that. It took 2-3 years to put it all together, but we published the results in spring of 2019. And so with these 2 battery-free wireless devices, one mounted on the chest, one mounted on the foot or the hand, we can reproduce everything that's done with wire-based systems, even in the most sophisticated NICU units, level 4 NICU units that exist in places like Lurie Children's Hospital in downtown Chicago. So this device goes on the chest. It monitors ECG, and so you can see the magnetic loop here. This is for wireless coupling. We have an NFC link that does data communication. So this same antenna, that loop is harvesting power and also serving as data communication link, wireless one. These 2 pads serve as electrical interfaces to the skin of the chest and allows us to measure, as I mentioned, electrocardiograms. And so in all of the experiments, and we are IRB approved on probably 200 premature babies, no adverse events, we're measuring with our devices. At the same time, the babies are being monitored with the standard wire-based system. So we have a basis for doing quantitative comparison of fidelity and noise levels and intermittency and this kind of thing. So this is what it looks like. This is the raw data coming off of this device. This is the clinical standard data. So very, very nice correspondence there, collected simultaneously. So from these data sweeps, you get obviously the heart rate variability very, very accurately from the R-peak and the QRS complex. You also get respiration rate by looking at how the amplitude of the R-peak changes over time. So that's heart rate variability, respiration rate. From that sensor. There's also a digital IC for doing temperature sensing as well. And the temperature at the chest of baby in an isolate is pretty close to the core body temperature. So that's how that part of the system is working. But it's binodal, have a separate device, wirelessly time synced with the first one. But the second one operates based on optoelectronics. And so we're doing reflection mode, photoplethysmography. And so from those data streams, we get blood oxygenation, which is another vital sign that has to be measured. in these patients. So again, it's wireless and battery-free. You can see the magnetic inductive coil here for power transfer and data communication. A pair of LEDs here, one in the red, one in the IR. They're flashing on and off out of sequence. And then we have a photodetector monitoring the backscattered light, and this is kind of what the raw data streams look like. From the oscillatory component, you get blood oxygenation. So that's how it works. This is an example picture of a device of this type on a 27-week gestational age baby. You can see the chest unit here. You can see the lineaments on the foot, but you can see that there's the leads for measuring ECG using the conventional approach. This is the hand of Aaron Thomas, who's head of neonatology at Lurie Children's Hospital. He sort of set the scale here. But this is sort of what it looks like, how it operates. We started out in the NICU. The nurses were so happy with the devices, the neonatologists and so on, that we actually expanded out into the NICU. So this is a pediatric intensive care unit, slightly older patients in that part of the ICU, but also patients who can benefit from a wireless approach. You can see the device on the chest, again, heart rate variability, respiration rate, core body temperature, and then the device, in this case on the foot, that's measuring blood oxygenation. So the transmission antenna is in the base of the chair in this case. And so it's coupling power up and it's pulling data off of these two devices. Again, time synchronized, so we actually go beyond the kinds of measurements that are done in a NICU or PICU today in the sense that we get hemodynamic information. So we can determine when a pulse of blood is initiated by a cardiac cycle by looking at the ECG here and looking at the time delay associated with the measurement of that same pulse of blood at the foot. We can get the pulse width velocity, which in many cases is a good surrogate for systolic blood pressure. So maybe a cuffless beat-to-beat blood pressure monitoring capability, going beyond what's done in the NICU and PICU today. So you start out with what's done today and try to build on that and go beyond. So here's some of the raw data that's collected. This is sort of the next-gen device published a year later. This platform is the one that's commercially deployed at this point, 23 countries, including lower and middle income countries. I won't say much about that, but the cost structure is also much more attractive. And not only do the wires go away, it becomes a much more appealing platform for monitoring vital signs in these babies, but it's also much lower in cost, to the point that you can deploy in countries like Zambia, Kenya, Ghana, India, Pakistan, and Mexico, which is where we're deployed currently. But this is the ECG data I mentioned before. These are the two wavelengths associated with the photoplasmography, from which you're getting blood oxygenation, and also the time delay here gives you that pulse wave velocity. But going beyond, you can include a high bandwidth accelerometer as well in the chest unit, so you get cardiac sounds. Again, that's not measured today, but it's important because it gives you timing information when the valves are opening and closing, and other kinds of cardiovascular signatures of health are embedded in the cardiac sounds, not present in the ECG, for example. So it's like a digital stethoscope in a sense. You can also get chest wall movement, so a redundant separate measurement of respiration rate to compare with the respiration rate determined from ECG. So there's tremendous amounts of information content in these raw data streams. Currently, clinical care just involves distilling all of this information down to very primitive parameters, so heart rate, SpO2, respiration rate, and temperature. So I think there's a lot of opportunity for using machine learning techniques to pull out additional insights associated with the detailed shapes of these waveforms, for example, and that's something that's not being done today, but I think it's a frontier opportunity. So tremendous things that you can do with battery-free systems in monitoring of parameters related to physiological health. But you might think about not only expanding the range of sensor modalities, but also thinking about these devices as a way to provide awareness to the patient around their health conditions. So thinking about haptic actuators you might be able to put into these devices to activate mechanoreceptors in the skin and create sort of a more meaningful awareness of health status, provide information through the skin interface. And those kinds of devices also benefit from a battery-free mode of operation for the same reason the sensors do. You don't want to load the skin with extra mass and volume that would otherwise be required with a battery. And so not only in the space of the healthcare would a haptic-based interface complement the kind of sensor functionality that I just mentioned to you, but in terms of a lot of people talking about the metaverse and virtual and augmented reality, currently dominated by visual and audio cues. But if you could add to that, a sense of touch, not only at the fingertips but across the entire body, that might be an interesting thing to contemplate in application spaces beyond medicine and healthcare. And so there we've also spent quite a bit of time thinking about how we can leverage our capabilities in soft electronics to not only do sensing, but also to provide a form of therapy through vibrohaptic engagement with the skin. And so here we have a very simple but scalable arrays of tactile actuators that we put in an array configuration, and then we put control electronics and power systems, wireless battery-free power systems on the back side of this thing, the back plane. And then we can control in real time spatiotemporal patterns of actuation. So you really get sort of an artificial sensation of touch that can be controlled either through a computer system or remotely through a touch screen, for example. But all these same ideas in hard, soft, hybrid electronics come to bear to enable sort of a soft, compliant platform that can interface with different regions of the body, different anatomical locations, but now coupled to actuators rather than just sensors. And so here again, we're just using magnetic inductive coupling schemes for power transfer and control, NFC. So we're doing power delivery and then NFC bidirectional, in this case, communication. So we send commands and then we get information back from this haptic interface. So just another area where wireless power turns out to be really important. So we spend a lot of time on graphical user interface and very low latency, about 10 to 20 milliseconds, almost real time. It's hard to notice any kind of delay. You stroke your fingers across the touch screen and that creates a corresponding pattern of vibrohaptic actuation at the surface of the skin. So you think about entertainment, gaming, obviously, but social media, remote interactions where you want to go beyond just visual and audio cues to something that would produce an effective sense of touch as an additional application space beyond medicine. So the other thing you can think about in terms of wearable devices are devices not only that are soft and sort of skin compatible, but also highly miniaturized is the other thing that comes as a consequence of eliminating the need for battery. And so we've thought a lot about that as well. This will be a nice simple transition to the neuroscience research platforms that I'll talk to you about in a couple of minutes. So we've been interested in sort of millimeter scale NFC technology where we have our magnetic inductive loop here, and then we use NFC system on a chip technologies for control and providing functionality in this context. And the reason why we think this is interesting is that as you reduce the overall size of the devices, for applications that don't require a spanning aerial coverage like a vibrohaptic interface does, then it opens up unusual points of interface with the human body. So you can take a device of that type and mount it on the fingernail, for example, which might be an attractive alternative to the skin for certain kinds of sensing, where you don't have to worry about nerve endings or sweat glands or exfoliation of dead cells from the striatal cornea. You can put it on the fingernail. And then the very low growth rates of the fingernail allow you to keep the device there for many months at a time. And the fingernail, of course, is transparent optically, so you can think about that same type of photoplethysmography being performed on the tissue at the nail bed using an optical interface right through the fingernail, where the fingernail is sort of acting as an optical window. And so we're able to do that. So same kind of measurement approach, red and IR LEDs flashing on and off out of sequence, reflection mode, photoplethysmography using an embedded photodetector, all controlled with NFC SoC, and then powered by inductive coupling to the coil. And so you can do this, and that works pretty well. And so you might imagine, this on a fingernail, and then with an ability to measure PPG continuously. So I've lost some movies here, but you can imagine putting a coil in a mouse or underneath the desk and do things of that sort. So that was sort of 2017. We were shortly thereafter approached by L'Oreal, which is a company that has probably very familiar with folks here in France, but that has a big business in artificial fingernails and through their Essie brand. And it turns out that some of those nails are quite expensive, like $5-7 bucks a piece, which is amazing. And so they were asking whether we could instrument those fingernails with this sort of technology, and that seemed like kind of a cool opportunity. And we asked them, well, what do you want to measure? And they said, well, we're not that interested in heart rate or blood oxygenation, which is what these devices do. We're really interested in measuring UV exposure because we have a big business in sunscreen. And so if we could create an awareness around our customers as to solar exposure, maybe that would drive enhanced sunscreen sales. And so that was kind of interesting to us, and so we began to think about that and put this together. So it's a battery-free device that is using NFC to do readout and then using sort of solar power to operate the dosimeter. So we have a photodetector here. We actually use an LED in reverse, responsive to UV photons. And those UV photons create a current that charges up a supercapacitor. And then we can read out the voltage that's accumulated on that supercapacitor via an NFC link to determine the total dosage of UV photons that has been accumulated over some period of time. And then we use a GPIO out of this TI NFC SoC to discharge the supercapacitor by activating MOSFET, sort of reset the system. And so the advantage of this is there's no on-off switch, there's no battery, it's always on, and it's highly miniaturized, and also extremely accurate because it's continuously measuring UV exposure rather than intermittently measuring UV intensity and then extrapolating dose, which is what conventional UV dosimeters do. So you can put all that together in a fingernail format. You have a pre-curved device, and we built that and launched it in 2018 at CES, and so a lot of people were interested in that. L'Oreal ended up making a product out of that. They decided not to put on the fingernail though, because they did study groups and found out that none of the males would put anything on their fingernails, so they lose half of their market by doing that. But they did launch the device about the size of an M&M candy, and then attach a clip to it so you can clip it on your glasses, sunglasses, or on your jacket or on your shorts or something like that. Put together a nice app. This was launched in all Apple stores across the U.S. and made available through their website. So it was a pretty cool technology. Worked extremely well. We provided this piece. An interesting side note here is the bill of materials for that device about $3. They sell it for $60. And Apple gets half of the margin, and then L'Oreal gets the other half, and we get a very, very tiny fraction of the whole thing. But this is interesting use case, however, because overall the customer response was positive, but two problems. One is that this clip had to be designed so that it didn't interfere with the NFC link for reading out the accumulated charge on the supercapacitor. So it had to have this sort of open design. It was made out of steel, and so it would tend to plastically deform after you use it a few cycles. And when that happens, then the device, it's very easy for it to fall off. And because it's so small, you end up losing it. And a lot of people are quite pissed because you lose your device. It's $60. It's not cheap. So that was a big issue, and it does speak to sort of wireless power in the sense that, like, how do you actually implement it in the real world becomes really an important thing to consider. So just sort of an anecdote around that. But we're also working with them on other kinds of devices. They're very interested in skin hydration. Again, they sell moisturizers, skin cream, that kind of thing, and being able to do spot measurements of skin hydration turns out to be very important. We have a NFC battery-free device for doing that, published more recently, but it uses a thermal dilution approach to measure thermal conductivity, which is correlated to water content in the skin. So it becomes a very, very simple type of device that couples to the phone, allows you to determine the hydration level, and then it recommends what sort of moisturizer you need to apply to your skin. So anyway, some things in healthcare and different sorts of skin interface devices. I'll talk now about implantable systems for biomedical research. And so these same ideas in skin-like sort of soft electronics work well inside the body as well, as you might imagine. So I talked a little bit about brain interface devices to interface with the heart. Lots of things you can do here in terms of electrical measurements, electrical stimulation, but optics turns out to be very, very important in neuroscience these days because over the last 10, 15 years or so, the neuroscience community has developed genetic techniques for creating light sensitivity in targeted cell types, neurons with certain cell types that allow you to either stimulate neural activity or inhibit it by shining light on these genetically modified neurons. So they express light-sensitive ion channels in their membranes. They can be activated with photons. That turns out to be very much more powerful than the traditional techniques where electrical stimulation is used to silence or activate neurons, because it's cell type specific and eliminates a lot of the parasitic effects associated with electrical interface, such as eddy current, heating, and so on. But the problem is, how do you get light into the brain to take advantage of this light sensitivity? And that has traditionally been done with fiber optic approaches. You have an external light source, pipe that through a glass fiber that's plunging down to the region of interest in the brain, and then affixed to the surface of the skull using dental cement and a commutator just borrowed from the telecommunications industry. So this sort of works, but the whole point of these sort of optogenetic studies is to look at the effects of the behaviors of animals on turning on or off certain neural circuits in the brain. By doing that, you can begin to tease out how the brain is operating. But if you're looking for behavioral responses, you have to consider that the fiber optic tether itself can modify behaviors, because there's mechanical load and physical constraint in natural movements. There's an inability then to also use optogenetics to study social interactions, because a pair of mice with these kind of fiber optic tethers in the same cage immediately get tangled up with one another. And so we began to think about whether we could create a battery-free LED that could be implanted into the brain to eliminate the need for the external light source and the fiber optic system. And mice are really small animals, and if you want to create enough power to run an LED over a reasonable amount of time, batteries are not a good option. And so the question is, can you deliver power then wirelessly in an ultra miniaturized platform that could be completely implanted under the skin and then tied to the LED, which is implanted down into the depth of the brain. So you can do this with far field wireless power transfer, which is what we're doing here, or near field techniques tend to work a little bit better, a little bit more practical in many instances. But they do open up opportunities for all sorts of neuroscience studies that can't be supported by fiber optic type approaches, and social interactions are one of them. Understanding the behavior of an individual brain is interesting, but the social brain is maybe even more compelling. And to understand how the brain operates during these interactive events. And so here we have a transmission antenna on this side of the cage, and so whenever the animals enter this part of their environment, the LEDs are automatically activated and stimulate or inhibit corresponding neural activity in the brain. But the other thing you can do now is you can put light sources anywhere across the animal's body. You don't really have to worry about complications associated with a fiber optic cable coming out of a soft tissue location like the hind leg. If you want to do optogenetics of the sciatic nerve, now you just have a soft battery-free wireless implant you can insert in that location, or you can interface LEDs with the spinal cord as well. And in all cases, really no measurable effect on the locomotor behavior. So here's an animal with an implanted battery-free wireless LED in the hind quarters, in that soft muscle location, running on a wheel without any noticeable change in its gait. And so that's sort of soft mechanics, battery-free, all these things are critically important. But the other thing it allows you to do is think about animals beyond mice. So you can do birds, bats, snakes, fish, all kinds of different things are compatible with this sort of NFC magnetic inductive coupling approach for power delivery and control. So these are zebra finches with LEDs in their brains, and then wirelessly controlled. You can see the antenna running around the cage right there. So that's the way it works. And we've been able to collaborate with the neuroscience community to begin to do real experiments, in these kind of social interactions. And so in this particular case, we have LEDs in a part of the brain that is responsible for the creation of dopamine. It's a neurotransmitter that creates a pleasure response in the animals. You do all sorts of things with that, and one of the things that we've done here is we've demonstrated the ability to program social bonding. So if I activate the LEDs in animals A2 and A1 whenever they're in proximity with one another, if you do that for a long enough period of time, it's creating dopamine whenever they're associated with one another. They will form a natural bond that will persist beyond the period when you're using that optogenetic trigger. So you can create friendships between, say, A1 and A2, and then you can allow those bonds to dissipate and then reform bonds between other pairs of animals in the social group. So all kinds of pretty interesting neuroscience experiments become possible. So partly because of inbound interest from the community around these kinds of technologies and our inability as a research group, an academic group, PhD students and so on, to engage with more than 2 or 3 different groups, we put together a very small bootstrap company and sort of commercialize the devices. And so at this point, there are 254 systems deployed across 108 labs in 8 countries, and we've sold more than 20,000 of these implants. So just single-use implants, essentially what they are. Advanced flex PCB manufacturing techniques are used to create those. So this is quickly becoming the standard for optogenetics research in neuroscience, just to give you a sense. And again, you can think about more sophisticated versions when you incorporate NFC technology and system-on-a-chip NFC platforms. And so here we have an array of LEDs mounted on the cortex, and we can program the illumination patterns across the surface of the brain, not just in one location with an implantable LED, but sort of across the surface of the brain in different sorts of patterns. And then looking to the future, we also have microfluidic technology. So now we can do optogenetic modulation of neural processes, but also pharmacological as well. So we have a pair of reservoirs mounted in the device. We have electrolytic pumps, all powered wirelessly, and we can program in the delivery of drugs down the microfluidic part of these probes, co-located ultimately with these microscale LEDs to sort of modulate neural processes using both of those types of schemes. And so this is for unpublished work, but it will be made commercially available through the same company, Neurolux, as well. A lot of interest in that. So it's not just optogenetics, we do program drug delivery as well. And so with the last 4 or 5 minutes that I have, I'm going to talk about this next area of bioresorbable electronics and what might be coming in the future. Again, a space where battery-free sort of wireless power transfer turns out to be critically important. So coming back to this slide, these implantable devices, you can think of them in 2 ways. One as either an advanced surgical instrument or surgical diagnostic, in which case the devices need to reside on the soft tissues maybe for a few hours, whatever is the intraoperative time scale, that kind of thing. And then they can just be physically removed after they've been used. That would be one regime of use, sort of short-term level of integration. And then the other possibility would be chronic implants. So think about a very advanced pacemaker that's pacing not only based on a single location, but maybe a pattern of electrical stimulation around the upper part of the surface, just thinking of it in terms of the future, in which case you want the devices to last life of the patient. So those are the 2 bookends in terms of time of integration, very short intraoperative and then sort of life of the patient. And for a while we thought that's all there was really in terms of implants, those 2 regimes. But it turns out that there's a whole middle ground where you'd like an implant to be temporary. So it would operate over a time scale correlated to a natural biological process, let's say wound healing, for example. Now, once the wound is healed, you don't need the device anymore. Ideally, you'd like it to just melt away and disappear to eliminate unnecessary risk and device load on the patient when the device is no longer needed, and also eliminate the need for surgical extraction. So that's kind of the motivation behind work around the idea of electronics that are dissolvable. And it's sort of a subset of a more general class of technology that we're referring to as transient electronics. So any electronic system that fully or partly dissolves, resorbs, or otherwise physically disappears at a programmed rate or a triggered time. Now, I'll really focus just on bioresorbable, but it's really a broader notion that we're talking about here. And so implantable therapeutics, diagnostics, that's what I'll focus on. But things that deploy into the environment, or maybe even reducing electronic waste associated with discarded consumer electronics. We got started because there are a lot of military applications, so I can't talk about those, but you might imagine security issues around sensitive electronics that are deployed at a distance in the field, and unwanted recovery by an adversary, and transient electronics might be important there. But I'm going to just focus on this one. And I won't say much about the underlying material science. This is a space we've been working on for about 10 years. There's a full complement now of materials that are environmentally benign, biocompatible, but that can support sophisticated levels of electronic functionality as temporary implants that disappear over time. So let me give you two examples where wireless power is very important and devices are addressing a specific clinical need. So we work with neurosurgeons at Washington University who are experts in treating damaged peripheral nerves. And so if you get a damaged peripheral nerve, if it's very severe, you go into the emergency room, they take you into the surgical room, and they'll open you up and then they'll suture the damaged nerve to sort of repair it, illustrated in cartoon form here. And then what's known in the neurosurgery community is that if you electrically stimulate the nerve at a proximal location with just a couple of leads and then a handheld stimulator, if you do that during the intraoperative period where you have access to the nerve, you can accelerate the rates of healing that occur. And so the idea here was that maybe you could take advantage of that with a transient battery-free piece of electronics that allow you to stimulate the nerve beyond just that intraoperative period where you have physical access to it, to dose out that electrical stimulation at different time points throughout the entire healing process. And that was the hypothesis, is that might further enhance the beneficial effects of nerve stimulation. So the scenario is this: you have a crush injury or transection injury, you come into the hospital, they open you up, they suture the nerve, and then they drop inside the body cavity a wireless battery-free transient bioresorbable stimulator at a proximal location. They suture you up, and now with wireless coupling, you can stimulate at different time points with different doses. And then ultimately the device disappears and resorbs after the nerve site has healed and the device is no longer needed. That's critically important. If it required extraction, it'd be a big problem because